So good afternoon, everybody. I have a pleasure to be a chair of this session of soft computing with applications. We have 5 presentations. Everybody have 20 minutes for talking and 5 minutes for questions. So try to be precise because we try to finish at 6 because at 7 we have a social event. Okay. And after 50 minutes of the presentation, I will show you the card that is 5 minutes left. Okay, thank you very much. The first presenter.
Yeah, shall I take this or this is fine? Yeah. Thank you. So I'm Nitin Satpute from Technology Innovation Institute. Today's talk will be on GPU4SNN. And it is basically GPU-based acceleration for spiking neural network simulations. So yeah, so starting with the overview of this particular talk, I'm going to tell you the brief info about the SNN and what exactly it is, how exactly it is important, and then the state-of-the-art approaches and also the proposed ones. After that, a grid stride loop, which is the basic contribution inside this particular approach. And then, yes, performance evaluation, and then conclude with some future remarks. So introducing the SNN simulation, why SNN? SNN is basically the spiking neural network, but why only SNN? We can go with the ANN as well. But the reason behind it is SNN is more robust because ANN can easily be fooled if you vary some input images slightly by adding some, by varying some input pixels. And also, it's a biological neural network. Like researchers would like to imitate the behavior behind the brain because brain is the most intrigued component of our body, and then the results that we are getting, they are more robust, accurate, and energy efficient. And if you talk about SNNs, they are less power hungry as compared to ANN, which is proven in our in the previous work, and also it is more energy efficient. So I'll just go, but the size of SNNs is quite high. So that's a big problem, and also the complexity it comes with. And the models inside the SNN is basically the number of synapses and neurons. It is the same as we have the ANNs, but here we have some internal model which decides how exactly the SNN should work. So these models can vary, and based on these models, we'll get the different results, different outputs. But yeah, as I mentioned, this is more complex network, so definitely it requires highly parallelized network, hardware equipment. Now we don't have anything to simulate the SNNs, and SNNs are basically the event-based operations. So based on the required hardware, based on the available hardware, we are trying to achieve as much parallelism as we can. So going with the SNN simulation, it basically consists of 2 important kernels, which are the update kernels and the propagate of a spike kernel. Now, what is spike? Spike is just a communication of information. The SNNs work based on the spikes. The way the ANNs works based on the input data, but for SNNs, the input is as a spike. The same way as quantum has qubits as an input, just to give you the brief info, brief relevance. Now, these are the 2 important kernels. Now, on a iterative calling of this kernel, what happens? You have to perform both of these operations: either update a kernel, update some neuron, and also propagate a spike whenever the neuron reaches certain value, certain threshold. So the communication is happening only when the particular neuron reaches certain threshold. So as I mentioned, any algorithm requires these 2 kernels to be implemented. And how to do that, we'll discuss on the SOTA and proposed algorithms. So in the SOTA algorithms, which are state-of-the-art approaches, there are basically 3, which is AND, S, and AP algorithms. So the AP algorithm is basically based on the event-based operations. So as I mentioned, SNNs are basically event-based handling. Now, what happens in AP? AP is basically active potential. Potential is another term, like SNNs is divided into three modular components. One is spike, but spike is generated out of current and voltage. So these are the 2 complex numbers, complex quantities, which define the SNNs. Now, as I mentioned, it is an event-based operation. Whenever there is a threshold, whenever the input crosses a threshold, there will be another event. So for that, on a GPU, when we implement it, we need a dynamic parallelism. So dynamic parallelism is nothing but the implementation in terms of the child kernels, parent-child kernels. But the problem with this approach is like how many child kernels you can have, or how many depth of child kernels you can have. So that limits the implementation, and we get the degraded in the performance. So we'll show that particular degradation as the spikes increase. Now, the next is basically a simple AS or AB. It's a normal parallelization. We identify how many computation parallelism we need based on the number of neurons and synapses. One way is we can launch number of neurons based threads and then iterate number of synapse times. So which is we call it as an algorithm. Another way is we compute total number of parallelizing threads, which is n into s, and then each thread will iterate one time. Now, the problem with this particular approach is the n by s threads. Can be way larger than the hardware resources which are available on the GPU or the number of GPUs. So that's why it's this particular thing degrades. This particular algorithm degrades the performance when your number of synapses and number of neurons are way larger compared to the hardware resources on the GPU. So these are the bottlenecks, as I mentioned, in physics, the complexity with number of synapses, because it iterates number of S times. And then S space complexity is basically number of neurons by number of synapses. And AP is with respect to the number of spikes, right? Because whenever there are events, the AP will come into a picture, and based on the number of depth of the, based on the depth of the child kernels, the performance of AP will degrade. Now, before in the proposed approaches, we have AB algorithm and the SQL algorithm. But before going to that, we'll talk about the important ingredient inside the AB and SQL algorithm, which we call it as a grid stride loop. Now, what happens whenever we launch a kernel inside the on the GPU? It's a responsibility of the GPU to arrange all the parallel threads or all the parallel computing blocks. So what happens? So you can see the first thing, all the blocks are randomly arranged. So out of 16 blocks, for example, if here there are 25 blocks and there are only 5 available computational blocks which are possible on the GPU, then these 5 blocks can operate randomly. They can define any random IDs and then they can schedule it. So behind the scene, there is a GPU scheduler which is managing all these details. So here, the constraint is basically the GPU scheduler takes some time in order to schedule and allocate the blocks for the computational events. Whereas in the grid stride loop, we just identify what are the number of parallel units available and how many number of tasks are required. So we just take into consideration, for example, 25 tasks, 5 blocks, we iterate 5 times again so that we can perform all the tasks again. So what is happening? We are already telling the GPU, okay, you don't need to schedule or allocate anything. Just perform the way we are defining it. So here, the random allocation is not happening. Only the way we are defining it in the form of grid stride. So in the dynamic scheduling, GPU controls everything. On a grid stride loop, CPU is controlling. In a way, the programmer is controlling it, basically. So let's go with the AB algorithm. Now, in the AB algorithm, what is happening? We identify how many resources available. For example, 5 computational blocks are available. And then based on the grid stride loop, it tries to achieve the required number of tasks or required number of events which it wants. So if it is 100, it will require 20 iterations, but they are defined. Like it will not happen in a random manner. So it's simple approach, which is the active block approach, which we call it as a AB. But the problem is it has to repeat from the CPU side. CPU needs to control like when to stop. So that's a controller bottleneck, which we call it as a CPU bottleneck, which we don't want. Now, as an alternative, we try to provide the SQL algorithm. Now, in the SQL algorithm, what happens? The objective is basically you launch a kernel and the GPU will take care of all the jobs. And then once the results are obtained, the final results will be sent back to the CPU. So here what is happening, you just tell the GPU, okay, you perform this operation the way he mentioned about, okay, you have to finish the task. He will not interrupt it in between. The same thing is happening here also. So the CPU just tells the GPU, okay, perform the task and don't come back to me for intermediate results if we want the final results. So this is how the SQL algorithm is implemented, which we call it as a single kernel launch. You launch a single kernel, and this particular single kernel will make sure, okay, both the update as well as the propagation kernel are happening iteratively on the GPU without any intervention from the CPU. But for SQL, as I said, it gives the final answer. So if we care about intermediate results, that's what the SNN is meant for, because we want the temporal variations. So that becomes a bottleneck. But anyway, I mean, if we want one or the other, we can play with that. AB and SKL. We will show that in the performance results, how they are matching with each other. And for a problem with the SQL is basically GPU resources. For example, if you don't have enough memory to perform a single kernel launch and operate all the results of once the computations are performed, then it can be a problem. Then again, you need to schedule via CPU, and the CPU will take a control. But that depends on how you manage the CPU and GPU bottleneck or CPU-GPU communications. So let's understand the performance evaluation. Now there are different firing modes. It depends on the how the encoding is happening. Now what I mean by the encoding strategy is it's a spiking neural network. The input is in the form of spikes. Whenever the image is provided, it has to be converted into spikes. Now you convert the spikes. Now what should be the rate of the spikes? The spikes are temporal inputs. Now it can be very high, it can be very low, or it can be medium. So we are showing first the medium firing rate for the spikes, and then we will show for the low firing rate and the high firing rate. So just to show you, the first name will be the winner of the algorithms amongst all five. For example, 2 proposed algorithms, and the remaining 3 are the state of the art. And the second will be a runner-up. So the objective of showing this is to show, okay, both AB and SQL are matching most of the times, or whenever they are not matching the performance, we'll show, okay, in these conditions, they are not matching the conditions. And 1.7, this is going to be a speed up. Anything above 50% will be highlighted in a dark manner. I mean, I don't know whether it will be visible here or not, but yeah, this will show the speed up larger than 50% speed up versus SOTA. So we will obtain the best of the SOTA and best of the proposed ones, and out of them we will take care of the we'll calculate the speed up. So this particular number is basically a speed up of best of both the worlds, like the proposed ones and the state of the art algorithms. So this green one is basically the SKL. So just understand, the green one is a single kernel launch. So you can see how with the variations of number of neurons and the number of synapses per neuron. Now we are trying to scale up the spiking neural network and check the performance, check the simulation performance, whether SKL is okay, whether AB is okay, or whether other algorithms, SOTA, are they performing well or not. So in this particular scenario, with this particular range of number of neurons and range of number of synapses, we find SKL is performing way better. And you can also see AB is also competing, like the runner-up is AB, but the SKL is giving the highest performance in comparison to SOTA. So the maximum speed up is 2.1, and then we again consider the other variations with respect to number of neurons and synapses, and we find AB is way better, and SKL is the runner-up algorithm. So they both are operating on wide range of number of neurons and synapses, and we find that they are performing quite pretty well. And here we are getting the maximum result as 1.7 times speed up comparison to state of the art techniques. Now here, when there are less number of neurons, and like if you see the number of synapses per neuron ranges around 2^11 to 2^13, the AP is performing well. Now why AP is performing well? Because the total number of spikes, the total number of events are quite less. So if the events are quite less, then the hardware scheduler on the GPU, it schedules way better. But as soon as we increase the events, I'll show you that, then AP degrades exponentially or quite rapidly. So in this particular domain, AP is performing pretty well. And then here we cannot obtain the results. The reason is the number of synapses are quite low comparison to number of neurons. So this is like not applicable reason. So this is the mode 1, which is a medium firing range. Now let's talk about the lower firing and the higher firing, like which is mode 0 and mode 2. So I'll just go directly through it. You can see in the mode 2, where large number of spikes are available, mode 2 is basically high firing rate, which is a large number of spikes are present in the simulations. So SKL and AB are dominating. SKL and AB are dominating. But in the case of mode 0, which is low firing rate, where less number of spikes, you can see the AP is dominating. But again, for some of the experiments, you can see SKL and AB are also performing well. So the proposed algorithm is quite good when you have high firing rates. And if you have a lower firing rate in the simulations involved, how do you know that? It depends on your applications, which kind of application you are involved in, whether it is totally event-based or whether it is totally parallelized. AB and SQL algorithm perform best in the computationally intensive regime, which is high N and high S, many spikes. I'm just showing this was a 2D diagram. I'm just showing a 1D example as well, the performance. So that particular row I have taken as a 1D diagram, and I'm showing the 1D image out of it. So you can see the yellow. The yellow is basically going exponentially high because it's a AP algorithm, and this AP algorithm is checking, okay, the events are quite high, and for these events, for the spikes, the GPU is unable to arrange the resources properly. So that's why the performance is degrading a lot. But you can check the AB and SQL for a wide variety of neurons. For the various range of neurons, AB and SQL are always better with respect to the execution time, except the case of mode 0, which is less firing rate. Note divergent behavior of AP in modes 1 and 2. You can see that's growing exponentially. And then show a good scaling behavior in all modes. AB and SQL show the best combination of scaling behavior and execution time. So in conclusion, we discussed the kernels which are involved in the SNN simulation, the potential SOTA bottlenecks, the state-of-the-art bottlenecks like the AND, S, and AP algorithms, why they are performing less. And then we proposed the two AB and SQL algorithms and their advantages as well, and explaining the grid stride loop as a core element of that particular proposed algorithms. And finally, we also discussed the potential limitations of AP and SQL. Like SQL, when you don't have enough resources, so you have to go back to CPU, and CPU will control the strategy. For AB, it's anyway CPU control. So if you want to have final result, then what will you do? So intermediate approach you can also opt for, like after a certain number of time steps or after a certain number of iterations, you can go back to CPU, take the result, check the results, and come back again. So this is something also can be explored. Detailed comparison on DGX server with A100 GPU. So this is the performance results which we have shown on various number of neurons and synapses are basically on A100 GPU. 2D scans, the performance results in terms of 2D scans as well as the 1D scans, and then we have shown the maximum speedups which we obtain. And AB and SQL are performing way better when we have high N and high S kind of simulation strategy. And 1D scaling also shows favorable scaling of AB and SQL in all the modes. So I hope you all have understood. If you have any questions, please let me know. Yeah, thank you for your attention.
So there is a time for question.
Yeah, I've got a kind of more general question.
Yeah.
Have you ever thought about implementing spiking neural networks on some other kind of accelerator, not the GPU?
FPGA is another accelerator that we are exploring. But I mean, our aim was to come up with the analog implementation. Now, FPGA doesn't support that CMOS, doesn't support the analog implementation. It supports the CMOS-based implementation. So that's one thing that limited us in order to go with the FPGA. But anyway, even if we want to have a implementation, the CMOS-based implementation, the FPGA is something we are exploring. So in the next months or something like that, we will try to come up with the FPGA implementation of SNNs.
Okay, thank you.
And other questions? So maybe from me, short, can you show us again the slide with the when there is a visual comparison of previous and your methods?
Can you go? Visit. Oh, it should be fine. Okay. Okay, 2D diagram?
No, the visual comparison of the method of the of connecting the
Okay.
CPU and
And
GPU.
It's not going. Can you take it? Yeah, this one, I guess it's already there. Or can you go some more back here? Some more back? Yeah, this one. But it's not coming.
So maybe I will try to ask you about the slide.
Yeah.
So show us that in previous algorithm there was in each iteration.
Yeah, this one.
From some to time there was a contact between CPU and GPU.
Yeah.
And so there was my question is if there was an synchronization in this moment, and if yes, how you do this? That now there is only one kernel.
Yeah. Yeah, exactly. So the synchronization is definitely needed because we are trying to come up with the grid style loop where we are trying to schedule and allocate the jobs. So for that synchronization, one way is using the cooperative groups, which NVIDIA provides. Another way is using atomicity or using, we can define our own synchronization strategy. Now for the SKL, which is single kernel, for single kernel also we need the synchronization. That's where we can launch the update and the propagation kernel together. Both the kernels, if we want to combine, we need to communicate the important information from one kernel to another. So for that, in between that, we need to synchronize the blocks, synchronize the computational threads, and then we have to go ahead with the next iteration.
So synchronize the blocks simply by, so it's active synchronization. You connect them by instruction, if I understand well.
Exactly, exactly.
Okay. Another question?
So just adding to that, just like delaying whatever the blocks which are already are done with the computations and then waiting for the other blocks.
Yeah.
That's it. Yeah.
Okay. Thank you very much for your
Thank you.
presentation. So the presentation about unsystem inspired heuristics